Python. So, so the topic of the session now is Python. We had before a kind of theoretical session about HPC. Now I think the theory finish and all the session in this training event are going to be more practical. I've been asked here to give you an introduction to Python, but okay, it's not going to be really an introduction to Python itself, but it's an introduction to Python for high-performance computing, because this is the purpose of the training. So I hope many of you are familiar already with Python and use it. How many of you do you use Python? Okay, so it's a good percentage. So yes, in this, I will also mention some specification, but the focus here is how to get performance in Python and how this is with NumPy, and then how to optimize it with NumPy. So some basic knowledge of Python is required, and also some kind of basic knowledge of NumPy. Okay, let's start from first an introduction, just to put everybody on pace, and then we go to the practical part. First of all, what is Python? Python is not a programming language meant for high-performance computing. And then you will wonder, why are we doing Python in this training event? The point is that almost all of you, anyway, as we saw now, but in general, most of you are going to use Python anyway. So Python is a very good programming language, and it's not meant for performance. It's meant to be a good programming language that is user-friendly and easy to use. And the purpose of this training is not so much about show you an HPC programming language that could be C, C++, but to show you what you should not do with Python when you use it for HPC. Because Python, since it's not meant for performance, can be very, very slow if you do the wrong things. So here, the purpose of the training is on how to use Python for high-performance computing. And indeed, it can become fast. It's not slow, but Python itself, pure Python, what is the Python programming language? It is slow because it's interpreted, many reasons that we are going to see. And you need to know what to do. Why Python? Why? I think all of you have a good reason for using Python in your research. Maybe it was suggested by your supervisor. It's something you learned during your master, etc. And the reason why, in general, everybody is using Python in data science, I don't want to say everybody, but almost everybody, as shown indeed in this graph, where Python is the most used programming language in data science, is because of many reasons that made it successful. So one important reason is that it's interpreted. So you can execute your code executes in the meanwhile you write it. And it's very useful this for debugging, testing code, etc. And it is one of the reasons why it's so used also for teaching. It is science and data oriented. It's plenty of packages that you can use for your computations. It's easy to learn. There is a huge community behind, and you can see here also a huge community that answers to your question. This is the number of questions on Stack Overflow for Python, and it's there is a very huge resource for finding any of your problems, for finding a solution to any of your problems. And it is the first choice for big data machine learning. And I believe many of you use it for this purpose, because you want to do some machine learning. And then it is very used to deploy software and so install them, like you most probably already tried by just doing pip install, you install any of these packages. And most of the times there are no issues. And so it's for this reason, it's great. On the other hand, it does not perform well. So it's very well known that Python is slow. So this is the key component that we want to focus on. Okay, how to learn Python? I don't know what stage you are, but here I try to classify what are the possible stages of your Python experience. You maybe start from having some code that you copy and adapt. You want to start breaking down. But I believe the level you should all try to reach is the level where you are able to write new code from source. And this is something that is not quite simple task. So it's easier to start from ready code, but often for your problem that is unique, you need to write your code. And for that, you need to go over all these steps where especially you have good knowledge of other packages. Today we will see two of these, but Python is great also because of the big availability of packages, and they have very good documentation that you should spend time reading, and they're very useful for that. So here are some stages. I don't know where you classify, but yeah, this is my case. Okay, I believe to have done all these steps. So we said Python is slow. So how should you use Python in your in HPC, especially, and also in everyday usage on how to for your problems? So Python, it's mostly meant as a programming language for logic abstraction. So what you should do is to write in these scripts the logic, the steps that your program should do, but never try to do the calculation yourself directly in Python, but always rely on other packages to do this calculation, like using NumPy for operations or many others, PyTorch for machine learning. You should never try to program the whole application in Python because this is going to be slow. So the purpose of Python is to be used as the logic for building up the logic of your program. And this is where it's very great because it's abstract and very dynamic and allows you to do very easily many complex tasks. But on the other hand, you should always rely on compiled code and backends for doing calculations. How do you know if they're compiled? Well, most of the time they say it, that these packages performance in mind. And compile means that they have an API, a Python interface that you can use. But on the other end, behind, everything is run on compiled code that runs very efficiently and fast, and was written most probably in C, and it reaches high performance. So Python is slow because one of the major reasons is because it's interpreted. Interpreted, what does it mean? So you're writing, if you need to think a bit about what your computer goes through while you're writing some code, basically you are writing some operations, you're writing some source code, and what are the steps that the Python interpreter has to do for executing it? Well, it should parse it, find possible errors, understand what you've written, and translate it in what is known as bytecode. So bytecode is some intermediate Python code that has very specific instructions. Then this bytecode is run to the interpreter that does some of this operation. The interpreter will use some compiled libraries and will mix everything together. So we'll do an operation at a time in this loop for then producing results. Instead, it's clearly that when you write a code in C or C++, you compile it, and this is where compilers are needed. You compile the code then runs directly on the machine without any intermediary. So it's just a compiled code relies on compiled library, produce machine code that produce results. So a compiled code is fast because it does not have all this part. And this is the part that makes Python kind of slow, but it's also the advantages of Python. So it's both a bless and okay, so how to optimize Python? The optimization, as I mentioned, it's to avoid as much as possible the interpreted part and rely on compiled libraries. Like we are going to see, for instance, when you use NumPy, you are just sending one instruction through this process, and then NumPy will take your data and use compiled code for producing the result directly, without having to be interpreted in the middle steps. So it's good because it does most of the calculation in this part with compiled application, and the interpreter is just used for starting the data. The key message that we will learn today is that in Python, you should never do for loops on data. Never. That is the biggest mistake you can do in your code that will make it very, very slow. You need always to find alternatives. And one of the solutions is NumPy, which is the first chunk of this presentation. And NumPy is nowadays the Python standard for numeric calculation on arrays, and it is used to operate on multi-dimensional arrays. Most probably many of you are already familiar with it. I don't want to spend some time on it because I think it's good for those that know it to have some more strong background on it, and also for those that don't know it to know that it's the major tool to use for it. On the other hand, it's NumPy has been so great in these years and created such a very nice API that has been used from many other packages as a base for their APIs. And so it's another good reason for having a good knowledge of NumPy in order to be able to use also these other packages. So it's important under many points of view. And now it's time to start on the practical side. So you can have we are going to use in this class collaborative notebook that is available on Google, unless this is useful because you find online already all the tools ready and you can run them without having to install them locally. If you have locally Jupyter Notebook installed, you can use that. Basically, now you should click on this link. And how can you do that? Well, you should probably go to the GitHub page of the event, unless these slides you already download them. So you can go to the GitHub page of the event. You can find it on our, the link is available. If you look for Castor C, I think this is the easiest way. You go to the Castor C website. You go to training. Where is the front page? Yeah, we go to the front page. Okay. Yeah. So.
Okay. So the GitHub page is on that. Click on that. Yeah.
Yeah. So if you go from the front page to the event 2022, you can find the Git repository here. So unless you want to copy the URL, you can find the Git repository here. You open the Git repository. This brings you to GitHub. GitHub is another great tool. If you never used it, it's something it's good to learn as well. You can go to the 03 Introduction to Python and what? Where? On which one? Once you want the presentation. Okay, sorry. Okay, let's go again. Let's try. You should be able to, but maybe depends on your. So one way, if you want to use it locally, you can directly download the notebook here. Otherwise, you open the presentation, and probably you cannot click it from here, but you can download it. So you cannot click it here, you say. Okay, but you can download it then. So if you press download, you download the presentation. And once you download the presentation, you can open it, go to the slide I was showing, and press the link. Or, yeah. So, and if you open it, you get access to the collaboratory notebook. And you should see these. Any issues on reaching the notebook? Here, online. Okay. So I think all of you could reach the notebook. So this is a notebook that you can use Unfortunately, to run it now, you will need to have, to use Google Collaborator, you need to have a Google account, so you need to be able to log in. If you don't have a Google account, then, well, I hope you have Jupyter installed and you can use Jupyter, or, well, we can discuss a bit when we arrive to the exercises on how to run it locally, how to install Jupyter, for instance. But yeah, if there are no questions, I will start showing some code and running it. If you want to run it directly, you can either run this notebook, but have in mind that this is, you just shared only a view, so the changes are not available online. You can though create a copy or open in a playground mode, and you can use it. You can use it in a new tab, basically. That it will not change the other one. Up to you. I don't know. Whoever used already Google Collaborator knows, or just to try to run it. So, okay. All good. Then let's start. Okay. Then let's start looking at it. Then don't scroll further. We will go step by step, and we go to different steps. So please follow all what I'm going to show you. The first very important part that we are going to focus on now is performance. Okay, I want to make you this to make you understand the statement that I said before, that Python is slow. So this is the first topic that we are going to see now. Let's consider now something very simple, that is an operation between two arrays or lists or vector, name them as you want, but two lists of numbers that have a certain size. We want to sum them and create a third one as a solution. That is the sum of the two. This is a very simple operation. So here I give you a few ways that you can do it with Python, with pure Python. For instance, a very first way that you can learn is to use you do a for loop. So this is how you do for loops in Python. Basically, we create an empty list in Y. Then we say for I in range. So range is going to give us the range of the numbers between 0 to the value that I'm going to give here. So in range 0 to the length of the array, what do? I append to Y the sum of the two component I. So this is going to create a new array that is going to have the sum of the two components for every place. Okay? This is one way to do it. A slightly faster way in Python is to avoid accessing directly the elements, like I'm doing here. And this loop can be optimized by using another built-in of Python that is named zip, that basically works like the zip of your pants, that is going to zip together the two arrays, element-wise. So if now I say zip x1 and x2, I'm going to get two components directly at these elements, and I'm going to sum them and append them to Y. This is a bit faster because it does less instructions. I'm getting directly the numbers instead of getting the index and then accessing the elements. Okay. I think the fastest way to do this operation in Python is the following. I would like to know if some of you knows a faster way of using pure Python, which is a compact for list creation. So basically, instead of having to do a for loop like this, I can create a list by just putting a for loop directly inside the list. So I say that I put the parentheses of the list. These are going to be the elements of each component of the list, so the sum of the two. And I do for I2 in zip. So I'm using the same here, and I move the components inside the list. So this is another compact way of doing this operation in Python. These are three ways that I have in mind to do the addition of two arrays in Python, and this is just using pure Python, okay? Of course, we are going to have a fourth way that is by just saying plus. So I have x1, x2, and I say sum them. Okay, this is the NumPy way. So this is something you cannot do in Python. You cannot have two lists and sum them, but NumPy does it. Okay. Okay, so if there are no questions about this code, please ask if you have any question here. By the way, do you all see well the screen, or shall I make the zoom in? You have it local, but maybe I make it bigger. People behind, is it fine? Okay. So these, if you don't have any question, let's try to run them. And basically, the purpose now is to measure the performance of each of them. Okay. Just a second, it's connecting. When you run the first cell, it's going to take some time because it needs to connect to a node. Basically, Collaboratory gives you the option of running on Google servers, and this is run there locally. So if you connect, it's asking for a node and reserve it for you. Now I'm connected. And this cell is run. I have a tick, and everything is executed. I defined 4 different functions. Now let's go to the how I'm going to measure the time. This is a bit more complicated. I will not go through everything, but just instantly creating plot, I'm going to use pandas. Pandas, it's something you are going to dive in on Wednesday on its usage for data science. So this is the topic of Wednesday. Pandas is basically creates a data frame, so it can store different data in a table like Excel will do. And then you can easily create plots out of it. Here I'm creating, I'm going to measure the timing on number of elements that are power of 2. So basically I'm going to measure timings on 2 to the 0. It is 1 component, 2 components, 4 or 8, etc. I go power of 2. And then I go for every size in this timing, I create 2 random arrays, and I time the execution of 1,000 times this function. So I'm looping over the 4th function, and I'm timing the execution of them. So I run it. This is going to take some time because it's going to reach some large size, okay? And now I can easily say to plot them, but first let's look at the numbers. So if I just say times, I'm dropping the column of NumPy to don't ruin any surprise. So this I'm showing the time for the first 3 only, okay? You can see that indeed we have run over this number of elements, 1 to 2048 elements at power of 2. And this is the time for 1,000 call of this function. So 1,000 times add 1, add 2, add 3, etc. Okay, and you can see that we are faster with going from add 1 to add 3. Of course, it's always better to look at figures instead of numbers, and I can say plot this data, and here I'm going to get some visualization of it. That really okay, it's not so nice. Maybe we run it again. Usually it's nicer. Just a second. Yeah, okay, this is much better. So because you can have some fluctuation in these time measurements, but what do we see here? So we saw that by increasing the number of elements linearly, the cost, of course, increase linearly. So you're doing more calculation, the cost, the time is increasing as well linearly. Okay. And we can see that we are actually speeding up. So we go from 0.75 seconds for this one down to 0.4 seconds. Okay, for doing 1,000 times 2,000 elements. And it's getting faster. Okay, by doing some optimization, we did a factor of 2 speed up. Okay. It's always good to also, no, yeah, but where do you expect now to be NumPy? I said it's going to be faster. How faster is going to be? Where will you put it? How much time is going to take for doing 1,000 times 2,000, so 2 million elements? Any guess? How many, where should it be the last point? somewhere here, 0.1. Where do you expect it? Let's see how fast it is. So now, so far I drop NumPy. Let's add NumPy. And how fast is NumPy? Well, it says that fast that you don't see the time. It's here, it's 0. But 0 doesn't mean that it took nothing. 0 means that on this scale, we don't see it. It's going to be non-zero, just it's difficult to see it. And for being able to see it, let's plot everything now in a logarithmic scale, okay? So if I plot everything now in a logarithmic scale, you start to understand better. And while the timing of the others is almost of order of seconds here, the time of NumPy is order of milliseconds, 10 to minus 3 here, right? And it's actually flat. You see, it's actually not growing here, okay? And it's much faster. You can see directly here that is 3 orders of magnitude faster than the other. So, few questions here. So we take order of milliseconds. Let's wonder if this is expected. This is what we will expect as a performance from our system. Then the other question is, do we like this figure? Is how we expect it? So I told you, and you all agree that it's normal that they increase linearly because we increase the size, the time increases. But why is NumPy the run of NumPy flat? Anyone has an idea? Please also online, if unmute yourself. Why is the time of NumPy flat? Because it's parallel computation? Not, doesn't do parallel computation actually. Any other guess? Why it takes the same time to do 100 elements, almost 300 elements compared to 1? Unmute yourself, so unmute the microphone so they can hear your live.
That for NumPy, just do the operation element-wise. So, for example, if we take one NumPy, let's say with 10 elements and another number with 10 elements, we just do, for example, addition, just do the same operation.
Yeah,
At the same
that's
time, because,
kind of, but the issue, why it's flat there, is because you're actually not seeing the cost here of doing, you're not measuring the cost of doing the addition here, but what you're measuring are the overheads of Python for actually telling NumPy to do that operation. So it's costing much more to Python to tell NumPy, add this to arrays and giving the arrays, etc., than actually summing them. So all this range here, what you're measuring are actually what are named overheads. So are constant costs that do not depend on the number of array, okay? Are constant costs that your program has in order to be able to run the operation, okay? So NumPy actually runs this operation much, much faster. Okay, we are going to see in a second how faster. Let's do now another kind of plot. This is time, okay? And now the other kind of plot is performance. Okay.
Sorry, Simone, I completely lost what you just said about the speed up. I got kicked off my internet.
No problem. So I said that I was saying that here that what you're measuring, why the reason why NumPy is flat is because you're actually measuring overheads and that the cost of Python for calling NumPy instead of actually doing the operation in NumPy. Okay. So now let's go to do another kind of plot, and the plot is about performance. So I mentioned, yeah, the question.
I was just thinking that, are we going to evaluate the performance of this, for example, the function that we are doing in terms of only the time complexity? Because I'm just thinking about the space complexity, for example, if what amount of space is going to occupy, because if, for example, the runtime is very small, but the space is growing exponentially, then I don't know. I'm just thinking that we should be doing two evaluation, the space and time.
Yeah, I mean, for the performance.
Yes.
So let's say that's kind of what people always worry about when they define the performance of a system, okay? But first of all, let's start from the definition of flops, okay? So the definition of flops, what are they? We said it in the previous presentation. Flops, that is what we are going to measure, are the number of floating point operation we can do per second. So how many floating point operation are we doing when we sum two arrays? How many? Anybody? How many operations do you do when you sum two arrays? Floating point operation. One. Indeed, you do 1 times the number of elements. It's not just 1. It's the size of the array. You do a size of array operations. Because you are doing the sum, you can see it in this loop, you are doing one operation, one floating point operation, but you do it for all the elements, so array. Okay. So when I define the flops here, what do I need to do? I need to take the size of the array, this is the size of the array, and divide it by the time. This is going to give us this performance. And you see that for NumPy, since the size, the time is constant, but the size grows linearly, or exponentially in this case, then the performance is growing exponentially. And this is something you always see in the performance graph, that is where, in presence of overheads, if you increase your size and the performance increases, means that you are measuring overheads. Because the performance, they cannot increase to infinite. The performance is a constant of your system, and it's how many it can do per second. So it's something that is an asymptotic function that will reach the maximum performance that you can do. And you can see that the performance of Python, this is not the performance of the hardware, it's the performance of Python. It's about, how many are these? Are 3,000 kiloflops, so are basically 3 million flops per second. That's the performance of Python as a programming language, not the performance of the system, okay? Are 3 megaflops. While the performance of NumPy keeps growing. Where does it stop? Let's see. So for not taking ages now, I will repeat the same exercise up to 2 to the 20, but only for NumPy, because if I run it for Python, you will understand that it's going to take ages. So if I run it only for NumPy now, these timings, we can see that, okay, we have some fluctuation here, but okay, we have this region where it's flat. We saw it up to here, 10 to the 2, and then it starts growing. Okay, starts growing linearly. So I believe we can also make it a bit larger, 21. And you see the last step, I added a step before, took a couple of seconds. The last step is taking much more now because I'm going a factor, an X power in performance, but you see that here then starts kicking in. So this is the region where where NumPy is performing up. You are actually measured the cost of doing the calculation. And if you extrapolate this curve back down, you see that the cost of doing the addition of one number, it's order of microsecond. Okay, this step here where it's flat, you understand these are two functions. It's one function that is constant, the cost for holding the function, and the other function that is like this, it's the function that gives you the cost for actually doing these operations. So when I sum them together, I have a flat region and then a linear region. Okay, so this is actually the graph you would like to see, where it increases linearly. And NumPy so starts to perform well with the order of 10,000 elements, at least, or hundreds of thousands elements. So this is where the size of data that you should use NumPy for. But you should use it also for earlier, because you see already here, it's faster than Python in all the range. So if you need to operate one element or 10,000, use NumPy. Just it's going to scale like a C code in this region. So this is the region where you should use Python for in general, because then you are not measuring the overhead, but you're just measuring the cost. And you can see that the performance reaches up to order of 10 to the 6 kiloflops, which is order of 2 gigaflops. And this is the performance of one CPU nowadays. So actually, in this region, Python is as fast as a C code. It's using optimally all the hardware. Just you need to use it in the correct range, okay, in the correct way. That's what I was referring to before when I was saying that you should not just do for loops in Python, never. This should be enough to tell you that never do for loops in Python. Always use NumPy as much as possible. And if you're going to use Python HPC, you should use it on a size of data that is large enough to not be affected by the cost of running the code in Python, but by just the cost of running a lot of data. So the fact that you have a lot of data pay off, and at some point, you don't see anymore the cost of running Python because this is a cost. Okay? Any questions here? So was it clear? Okay.
So beyond the 10 to the 5th, we should be using Python, not NumPy.
No, the opposite.
The opposite. Okay.
Yeah. Always NumPy, never Python. Okay. Hey, Jay, what maybe your question should be is above 10 to the 5th, Python performs as well as a C code. A C code here will perform better. A code written in C. So a compiled code. The fact that it's interpreted pays back. You don't see it anymore as a difference when you're here.
Mm-hmm. Okay, thanks.
If there are no more questions, I will move back to the presentation.
Simone, can you hear me?
Yeah, is there a question?
Yeah, I have a question. Marco here.
Hi, Marco.
Hi. Can you say that it's speeding up because it's vectorizing in general?
Okay, you're coming a bit low in volume. So you said about vectorizing.
Yeah. Is it because you're vectorizing instead of doing the for loops?
Yeah, okay. Okay, if you mean that by vectorizing, of course. The point is that NumPy runs everything compiled. So it's like running a C code from Python. So NumPy is compiled, is based on BLAS mostly. And the for loop, which is referred to as vectorization in NumPy, is run in C. So it's accessing the data and just run through them in C without asking anything to Python, and gives back to Python let's say release the GIL once it finished the calculation. So it's basically running everything in compiled code, and then it's going back to Python afterwards. So it's faster because yes, it vectorizes. I'm going to talk more about that. Okay, so we cover, I also have it here on the slides about these plots in case you want to look at them again later on. This is about performance. Now let's go have a deeper introduction to NumPy because it's useful to have a good knowledge also on how NumPy is working and what are its capabilities. Many of you probably know these details, but let's. I think you will find some new useful information on this. So, okay, I went out too early. First of all, how does NumPy work? So NumPy is meant for n-dimensional array. N-dimensional array is something that has many dimensions. It's not just a matrix, it's a tensor, something that has many indices. So for defining n-dimensional array, what do you need? You need a shape. We refer to shape as the shape of the array. You need a data type. The data type is how the array is stored in memory. So this can be integer, floats, many other ways, many other precisions. So this is the data type of the array. And then the other input that you need, but we're not going to focus on it, it's the ordering. So basically how the data are stored in memory. These are three objects that define an ND array. And it's what NumPy needs. And then needs the data. Based on this, then everything is run on this code with high performance, and it's and this is indeed the purpose of NumPy. So implementation-wise, we are going to see how it works in detail now, just to give you an idea, because I think this is very interesting. Okay, so let's go fast through these few steps that I mentioned. Okay, if you want to use NumPy, what do? you just say import NumPy as MP, as everybody does. You import the package with a different name that is named MP. You can easily create an array. So if you have a set of data, or you're loading data from some file, etc., you can easily load them inside NumPy, and NumPy will create out of this an array. Okay, so now I had a list 1, 2, 3, 4. This was a list. After an MP array became a NumPy array. As we said, this the information that this is taking out of this array are the shape and the data type. So the shape of this, what is it? It's 4 elements. The data type of it is integer because the data was an integer. Okay, so automatically deduce the data type and the shape optimally based on the data that you get. Okay, so then you can easily make this array multidimensional, and for instance you can say to reshape it, and if I say to reshape it 2, 2, I will have these 4 elements now ordered in a 2 by 2 matrix. So now I chunked it in 2 and 2 lines, and it is a 2 by 2 matrix. Okay. The same thing for reshape. I could let it reduce automatically the other size by putting a -1, and if I put a -1, it will divide by 2 and then find out what is the remaining, and we do the same operation. Okay. Or in the other end, I can change the data type. So I can go from integer 64 to integer 32. And now this is stored as integer 32. What is the data type? How many of you know the difference between integer 64 and 32? Anybody? So the data type is another very important knowledge in HPC, because if you change the data type, your code runs faster, but at less precision. So what is the data type? What is the 64 and 32 that it's written here? So 64 here are the number of bits. An integer usually stored as 8 bytes. 1 byte are 8 bits. 8 times 8, 64. So an integer normally is stored with 64 bits, and this is the size in memory of the integer, right? So you can the integer then, I don't know how many of you know the details, but when it's stored in binary format, each 1 0 indicates a power of 2. So you reconstruct the integer by doing 2 to the 0, 2 to the 2, 2 to the 3, etc. And the 1 0 tells you whether this power or not. Basically, it's written in binary format. Okay. And you can understand that going an integer that is 64 bits can store a number up to 2 to the 64. Actually, it's 2 to the 63 because the first number is used for the sign, while an integer that is up to 32 can be stored up to 2 to the 31 as a value. Okay. Of course, both of them are fine for doing 1, 2, 3, 4 because they're small enough, but smaller than 2 to the 32. But what is the difference? The difference now is that if you store the data in half integer precision, so this is named short, this will take half the space in memory. And it will run often double faster because the CPU can process much more numbers together. Okay? So this is why it's useful sometimes to store the data in lower precision, having in mind that you lose accuracy, so you can use only up to smaller number of data. But if you can do it, you can do it. And this is another important feature of NumPy, because in Python, this cannot happen. When you write 1, 1 is an integer, and the type of 1 is int, and there is no difference between short, long, integer, etc. And actually, Python uses a more complicated kind of integering, where you can store any size of integer, any number, and Python can still process it. So you're not stopped by the fact of doing 2 to that. This number still can be written in Python, and is an integer, and it uses as many bytes as needed. So Python is not also from that side. You cannot change increase the performance by changing the data type. The data type is fixed. Python decided. And the same is true for floating numbers. So if I write 1.0, now the type of this is float, And this is always stored in double precision, never in single. Even though it's in float, this is always in double precision. In NumPy, I can say both, I can have a float 32 or a float 64. And sorry, 34 doesn't exist. Float 32 or 64. And it's going to be a 32-bit float or a 64-bit float. And you see now there is a dot because this is a floating point. Okay? Any question? Okay. But how does NumPy work? So NumPy, we are going to see it's great for doing these operations, but how does it work under the hood? We said there is this compiled interface, and basically what all NumPy is going to use is it needs are this information and the data, and it's going to run the code. So if you want to learn more about it, there is this buffer protocol interface in Python, and you can get this information from the array interface. So basically, if now I say r.array interface, here I get the information the NumPy needs for being able to do operations on its compiled kernels. What do you need? You need this number, this weird number is the pointer. How many of you is familiar with C? Okay, few. So when you are storing data in C, you are going to have a pointer. So this is the place in memory where the data is stored. So it's pointing to that place in memory. Okay, so this is where the data is stored. Strides, we are going to see them in a bit. This is a description, it's nothing important. This is the type string. So this is what we said, this is an integer of 8-bit. Okay, this is the shape, and this is the version of NumPy we are seeing. So this is what it needs to store the data. What NumPy does, if now I take the same, like I did before, I create a new array that is reshaped like this, and I check the array interface, what did NumPy did now for me? Did it create a copy of the array? It did not. This array 2, it's pointing still at the same place in memory, okay? But now it views this data with a different shape that is 2 by 2. Okay, because from the NumPy point of view, and this is how these multidimensional operations work. For the NumPy point of view, these all arrays are actually flat, are a list of numbers, and whether these numbers are ordered as a 2 by 3 matrix or a 3 by 2 or a 2 by 3 matrix, it doesn't make a difference. It's still always unrolled. It's still 1, 2, 3, 4, 5, 6. It's just that you view it in different slices, and it's always pointing to the same data. Okay, this is very, very important to know, because often I know that many of you already, if you have ever used NumPy before, run into this issue, that often when you operate on these arrays and you change the content of the array, you need to be careful that if you did a certain operation, you're actually changing the content of all the other arrays that are referring to the same space in memory, because they're always the same array. So I think many of you are running this problem that when you are changing the content of the array and it's changing also other stuff that you didn't expect to change. And this is because of this reason, because NumPy never creates copy if it can. It just creates a different view of the same data. It's just a view. The data lives in C, are compiled, they live there. This is just an interface that you have in Python to use this data. This is why it's fast. Okay. So when you create the copies from the point of view of Python, they are different. They're not the same stuff. They're two different things. But often they are the same data. So for instance, if I transpose the matrix, okay, did NumPy create a copy? No, it's still the same pointer. It's just that now it's reading the array the other way around instead of that way. So very often NumPy will avoid to do copies, and you need to be careful about this. So it is an important message about NumPy and how it's working, because it's optimized in this way. Any question? So this is true also when we do item accessing now that I'm going to.
So Simone, how can you enforce NumPy to make a copy?
Ah, okay, good question. You need to say to copy. Either you do operation. So for instance, if I do r+1, okay.
Mhm.
So this is r4. Spelled. Okay, so it's not my keyboard. So if I do R4, different numbers, what do you expect? Different data. They cannot point still at the same data. Now the data changed, so there are new data in memory. So if you are doing some operation on them, and I say R4 dot, you can see that now the pointer is different. Now we're pointing somewhere else, the data is different. Or you just ask copy. So if I say r.copy, now this will do a copy, still the same data, but copy means copy. It's copy, okay? So these are new data.
Simone, if you don't do the copy and you define like before array 4 to equal array 3, and then you remove or you append some elements to array 4, would that change array 3?
No, because adding elements means changing the size, and changing the size means a new allocation of memory. So you cannot dynamically change the size. So that is, we create a new array. That is the size, that is the element. I mean, it's not always happening, just it's something that you need to have in mind, because very often your code is going to, you're going to have bugs because of this, okay? This is what I wanted to stress. So have it in mind that it's a bug meant for performance. So it is a performance optimization. As far as I can avoid to do copies, I don't do them, but you're still referring to the same space in memory, so.
So only these operations that do reshaping.
And there are many others. Also, when you slice the array, we're going to see it now when we access components. But yeah, there are various.
Okay, thanks.
Okay. So now let's see a bit about item accessing. We think then we'll stop here. So item accessing. Now let's create a set of data. Let's name them. Let's name it flat. A flat set of numbers. These are 90 numbers. Now we arrange that, and I want to reshape them in a way that I can reshape them. Let's say so 10 times 9. These are 10 times 9 matrix. Okay, so we have 9 column, 10 row, the 9 elements per column. Okay. Now you want to access elements. How do you do? So well, you can of course put a number here, and the first number will tell you the number of the row. You are always accessing elements from the slowest to the faster running index. So 0 means the first one, second one, etc. element of that shape, of that axis. So 0 is going to give us the 0 row, and the 5 is going to give you the 5th row. Okay. Or in the same way, now we can access a column. So we want to say with a column, with this symbol, we say, I want to access all elements of that axis and the 0 component, so the 0 column. So if I say now this is giving us the numbers 0, 9, 18, etc. Okay. Here, even if we slice now the array, most probably NumPy didn't create a copy. He still pointed to the same data, just taking a slice of it. Okay, so these are another thing. Okay. Now, I think many of you know this detail. So this is named slice, the one with open ends. If I want to take a specific range instead, not as a slice, I need to close both ends, like here. And so here I'm taking the second and third column. So you need to have in mind that always it's the last number minus 1. So it's 2 and 3. And we take everything up to 4. So this is still a slice, this is a range. If I do this operation, I get now part of this matrix that is the third and fourth line up to the fourth, this part here, okay? And so you can do some kind of this cool operation. And these are still pointing again, and I repeat myself, to the same data. So if now I do something on this, I'm going to change the data there. Indeed, I'm going to do it in a second. A few other tricks for accessing components. You can use none, and none will actually add an axis. So if I say none, I'm adding one axis at the beginning. This is for free. It's still the same matrix, just with one. Or I can use dots for skipping axis and then do something, e.g. none. And so if I take this, I'm adding one axis at the end. So this is just how you can do these things. If you want to set data, you just say the same equals something, and this sets some data to 0. What did it happen now? I changed the data in place. So what did it happen? That my original array that was named flat changed as well, and it have 0, 0. Okay? Here. So those 0, the fact that I added 0 changed the original data. Because this is just a view of the same data. So this is what I was referring to, that you need to be very, very careful. So if you change data to an array, you are changing everything else that was pointing to it. Okay, because these operations are in place. And the same is true if you do operations like plus equal, minus equal, multiplication. And you can see it here that, for instance, if I add plus equal 1 to the array, this is actually not creating a new array. It's still the same. I've incremented everything of 1. And in the same way, my original array is incremented with 1. Because I'm still pointing to the same data. Okay. We are 30, perfect timing. We are almost at the end. So here there is an exercise. There is an exercise for you that is about creating two functions, one named getRow, getColumns, which one returns the rows and the other the columns of an array. Okay, you should try a bit out. So basically, you want to use some of these functions. And since we are going to have now the lunch break, I guess, yeah, it's a good, if there's some time during the lunch break to try it out, or you want to do it now and get your lunch a bit later, it's fine. After we will start with completing these exercises. Here there is a description, you can read it, and there is also some extra that we are going to do. Okay, so let's, if there are no questions, okay, please ask questions, otherwise we go for a break. Any questions here?
I mean, can you avoid the last problem where you had flat and then you did something to a slice on array and change flat? Can you put something like a placeholder or something to avoid it?
No. The only thing you can say, but also this is a bit advanced, you can say that your array is read-only. So if I say that flat needs to be read-only, and this you can change it. I need to check how, but you can make flat only read-only, and this will not allow to be written. That's the only way to avoid it. That have in mind. If you make something read-only, will not allow you to change data in place, and basically we'll change this false to true. So the false here means that if it's writable or not, and if it's true, means that it's read-only, and so you cannot change it. Okay. So,
or you can just make copies and just be aware of.
Yeah, of course, you need to make copies. But if you want to be sure, give a back a NumPy array, make sure that it doesn't change, you can do like this. And if you look on right, online, you find us. It's a flag, yeah, writable equal false. The array.flags is this one, yes. So if I say array if here Linux, sorry, if I say r.flags dot writable equal false, Now this is not writable anymore. It wasn't like this. Writable. Okay, it's not working. I don't know why. Anyway, we'll check it a second now and let you know.
Okay, thank you very much.
Okay. Yeah, should be that. Maybe the version of NumPy here, it's different. Another question? Okay. Okay, anyway, it's fine. Yeah, so let's have a break and exercise, and we start with exercise.
Okay, so thank you, Simon, for now. Try your exercises during this 1 hour. We have now a break, and we'll meet 1:30, everyone. If you have questions, you can always unmute or ask any one of us around. Thank you.
This becomes useful in certain situations. It's a fast way to shape. Okay. And it's very similar what you do, but so yeah. Okay, we are going to be back in 3 minutes, so we can already maybe start discussing some questions if there are. In 3 minutes, we go over the exercises. Okay. Also online, if you want to ask anything, please go ahead. Okay, let's start again. So I left you with 2 exercises. The purpose of these were to write a function that gets rows and columns of a matrix. I saw some solution here around just to go through a couple of options that I saw. Okay, the purpose is to return a list of rows, right? So what we said before is that we can access a row of a matrix by putting a number